Welcome to this historic occasion of our first, Trinidad and Tobago's first PyData group. So, well, basically, we formed this PyData group because, well, mainly because of Torian's recommendation, because he was attending our TT lab presentations and he found them quite good and thought we could share our work with the wider community which PyData represents. So that's pretty much it. We hope to make a big impact and at least teach people, educate people on what we're doing here, because we're all just a bunch of data scientists, and data scientists like to share their work or our work. So our first presentation is Greg, and Greg, you can probably just introduce yourself and your topic as well.
Thanks, Rajiv. Well, my name's Gregory Ollivierre. I'm I guess soon to be recent grad of the data science program at UE. Before that, I worked in the oil and gas industry within signal processing, and I'm relatively excited to present some of the exploration I've been doing for the past 2 months. By no means am I an expert in everything here, but I think with Rapid's help, everything kind of seems to make sense now.
Rajiv, you want to read the conduct?
All right, basically, I'm reading this short version of the code of conduct here. First rule is be kind to others. Don't insult or put down anyone. Everyone must remember to behave professionally. And remember that harassment, sexist, racist, or exclusionary jokes are not appropriate. All communication should be appropriate for a professional audience, including people of many different backgrounds. Sexual language and imagery is not appropriate. So PyData and Focus basically is focused on providing harassment-free community for everyone. So it's a very inclusive community regardless of gender, sexual orientation, expression, disability, parents, body size, race, and religion. So basically just very nice, fair community, no harassment, safe space for everyone to share their work and act professional. So Greg, you can take it away.
Okay. Everyone can see my screen? Hello?
Yeah, you can go ahead, Greg.
Yeah,
cool.
Okay, cool. So today's talk is largely about GPU accelerating seismic workflows. So basic outline, I'll talk about why I was interested in working on this to begin with, what it is that I'm trying to achieve, talk about seismic data and its intricacies, some of the tools that were utilized to solve this problem, and then a few live sharing notebooks. So yeah, I think I went through some of this about me already. I did math and physics way back in the day, and only recently should be completing my data science. Chess, coffee, or travel, if you want to contact me about any of those things, be happy to chat. And I've worked in signal processing for 14 plus years. Right. So having worked in the seismic industry for a while, I've played with a lot of the data available, but I've gotten used to the idea of like basically sitting on a host machine and connecting to the data center to process a lot of what that seismic data had to offer. Some of that software was proprietary. There were a few communities coming out of Austin that, were more focused towards building specific tools, but we didn't have tools back when I started other than software that was purpose built for the data center. So I figured now, since I was working on some data for my MSc, like, wouldn't it be great to try to use GPUs instead? Because the promise that GPUs offer is quite great. So currently in a Python ecosystem, and I should put a disclaimer, like this is largely about the Python ecosystem. This is what we have. You'd read in most of your data. It may be seg-y, it may be seg-d. I'll talk a bit about what those formats are. They have attributes, and then they have actual like floating point arrays that refer to the actual data. And there's a tool out there called seg-y.io. It's currently what most people use in the Python ecosystem. There's another library that's less familiar called opspy, but for the purpose of this talk, we'll be comparing against seg-y.io. With this, you more or less just have an object in memory that you can play around with in SciPy or NumPy, and then you can visualize what you've played around with in like Matplotlib or Seaborn or something like that. So that's the current ecosystem. But if we wanted to GPU accelerate this, just one thing I guess I should say is that this particular workflow that I have on the screen here is CPU limited. There are some tricks that you can do in the modern era in the cloud to sort of like throw multiple CPUs at the problem. But this talk will be largely about, how we could potentially use GPUs in the cloud as well. So that attribute data to SegWi.io, which is the container that holds all of the SegWi data, that could potentially be accelerated by utilizing GPUs. A lot of those processes are parallelizable, especially the decoding process and the manipulation process, as well as the visualization and manipulation, because Matplotlib is not the only thing out there. And if you're dealing with something that's heavily parallelizable, as we'll see a bit later, then a lot of the display functions can be assisted with GPUs as well. So in terms of what I'm aiming for, this kind of gives away a lot of what was done already. But if you compare the top workflow to what I would hope to achieve, let's say in the bottom workflow, we're more or less utilizing GPU processes wherever we can currently. There's potentially space for a lot more. So I'll go into detail in what cuDF, CuPy, and X-ray are in the following slides. But for now, if we keep the goal in mind that it's roughly converting raw data to something that's structured, transforming it, and then visualizing it as a sort of basic pipeline process, then we're in a good place to like move forward through the rest of the slides. And GPUs are desirable because they're potentially able to scale a lot better than just pure CPU-bound processes. So before we get into that, let's try to understand seismic data. So the infographic on the left doesn't really do complete justice to the acquisition process, but it should help condense the idea. Realistically speaking, if we're familiar with the concept of an ultrasound to image, let's say, something within the human body, then seismic exploration is quite similar. Sound is emitted either on land or in the oceans, as the case may be, with the ship sort of sailing in sort of a racetrack style, so that it could build up a number of images or a number of data sets that look like the subset on the right. And the subset at the right just has a time to trace sort of layout, so that it can acquire all of these channels in like groups together, much like painting, a wall or something. You just kind of build it up one stroke of paint at a time. So seismic exploration, at least in the marine environment and also at land, kind of goes through that process of building up the image of the subsurface in this format. Then there are a number of different seismic formats available. SegWi is perhaps the most common, and I'll be talking about SegWi in this talk here. Right, so SegWi data, at least revision 1, there's some more modern versions of it, but this talk will be largely about concentrating on revision 1, is made up like the infographic at the top. You get this sort of first 3,600 bytes that are like a table of contents for a book or a novel in general, that tell you what the rest of that seismic data file should look like. So there's the file headers at the beginning, and then there are the data traces. So if we kind of think of it like the infographic I've drawn at the bottom, you have this little orange bit at the side that tells you what the structure of the blue and green bits are. So a number of green bits and one blue bit together make up what's considered a seismic trace. The blue bit is metadata. So it tells you some specifics about that trace, like how many individual blocks there are and how many individual of those green blocks, and some other useful things like, okay, well, where was this on the Earth? Like what was its latitude, its longitude? What was the depth of the ocean at this point? What was the sea temperature? You know, what bearing was the ship sailing on? All those sort of things in a marine environment. Oh, that metadata goes into that little blue block there. The green blocks is really sort of what these, if you look at the infographic on the right, those wiggles, that's what constitute like a number of these green blocks together. So they come together and they formulate what's known as a seismic section. And that section can represent many different things, an individual shot point, a common depth point, a stack, so on. So samples go from top to bottom, traces go from left to right in this infographic. But an interesting thing that really lends itself towards GPU acceleration is that those green blocks can be stored in different formats depending on the era and the dynamic range that you're looking for. So I'll go a little bit more into that now. So if you're only allotted 32 bits to represent a floating point number, there were a couple options in the past, and more or less computers these days tend to use IEEE. But in the past, there was a format called IBM. It was base 16 with a pretty wide dynamic range. The modern format, IEEE 32-bit, more or less is base 2 and has a smaller dynamic range, but there's less, if you think of a real number line, there's less holes, let's say. Segway.io is one Python library that exists that can read both of these formats. It's sort of built on NumPy and Python, so it doesn't have much problem reading these bits and interpreting them the correct way once you know what the correct format is. And by the way, the metadata also tells you what format the floating points are stored in. It's a CPU-bound process, though, so it can only scale that much. And to highlight one of the issues, why you would want to get the format correct, if we look at the same 32-bit structure in the infographic on the left, that floating point number is very different, which represents an amplitude in the subsurface. Those two amplitudes are quite different, so they're not even that close to each other. So it's very important that you get that right. So when I realized that this was one of the major early stumbling blocks when it came to decoding seismic data, I started looking for alternatives, because I was wondering if Segway.io could be made parallelized or if it could be done better or faster. So I started doing some exploring, and turns out there's a Python library called IBM to IEEE. It's a ufunc written in C, so it's pretty fast, but it is CPU bound. In the GPU world, there is Number and CuPy. And CuPy really turned out at the end, as you can see from the graphs on the right, it turned out to be the fastest option. But if we dig in a bit deeper, we can see that at the scale of 10,000 traces, CuPy is already the clear winner. Not by that much when compared to like IBM to IEEE, but it is, at least when I get to the notebooks, we'll see where the real power of CuPy comes in. So Number is perhaps a very nice library for approaching parallelization as a beginner, because for me, I realized that I could prototype something in Python, and with a few decorators, I can get comparable performance, already better than, let's say, Segway.io, with just a few lines of code. So I quite liked that experience with Number. But SegWire.io and most of the approaches that have been done, or at least that I've seen before, they work really well for small files. With big files that cannot physically fit in the RAM that you have available, we're going to run into problems. So one way I came across, or one way I started to think about how would you solve this problem, is if you could replace the disk file from an unstructured or sort of sequential format to something that is more parallelizable or easily parallelizable. And one of the key ideas behind being able to parallel read or write would be chunking. So you want to split the data set that you have into logical pieces that you can just address and play with without having to read the rest of the file. So in the infographic, we'll kind of more or less see at the bottom that the typical way to represent, let's say, an entire seismic section would be a multi-dimensional NumPy array, kind of like in the index order that you see here. But is there something that we could do to chunk a NumPy multi-dimensional array, or let's say 3D, 4D array, into something that's purely addressable? And that's where I came across this, well, there are a couple of formats available, but netcdf4 fit the use case that I was interested in. netcdf4 has multiple APIs, but luckily for me, it also has a very nice Python API. The fourth version is one of the more recent versions that follows an HDF5 model. It supports chunking. It's a very nice, simple API. It also supports writing and reading from the cloud. It's a pretty good abstraction for multidimensional data. Excuse me. And pretty, I guess if I can just go back to that slide, just to highlight the point, the metadata that's in those blue blocks there are now able to be kept together with their floating point relatives in the same space because of how netcdf is built. So as we'll see a bit later when we talk about Xarray, you can put a bunch of metadata in a dimensional structure and have them reference the underlying seismic data or floating point numbers that you're interested in. So they're kind of tied together with the same coordinate system. And that's pretty good for people that have used like pandas in the past. But netcdf is just one part of that. Getting that sort of nice pandas-like infrastructure relies on a sort of another library known as Xarray, which is also made in Python. It evaluates data that's on disk in a chunked manner, but it evaluates it lazily. So you can tell, let's say, what the size of an array is without actually ever reading the array. You can put processes together, like array.process, another array.process, another array.process, and then evaluate everything at the end because it's lazy evaluation depending on what your backend is. The currently the most popular backend for Xarray, which is a multidimensional ND labeling abstraction, is Dask, which itself is a CPU-based process, but it evaluates lazily and it can build these sort of process graphs together that only need to be evaluated at the end. If we have a quick look at the infographic on the right, we can read that netcdf file kind of that we generated here that's now on disk and utilize an abstraction of how the data is put together to just go straight from disk to plot with this new, if you will, pandas replacement. So any questions on that so far? Because it's time to go to a notebook. Rajiv? Shiv? Torin?
I think we're good.
I know I had a question, but actually maybe I should just watch you demo it first before I ask it anyway.
Okay. So this is sort of the, I guess, the entire workflow. You're still able to see my screen?
Yeah, it's fine.
Okay, cool. Yep. All right. So in terms of the previous way that this would have been done, I can kind of demonstrate that now. SegWhy.io is the library. There's a particular data set that's freely available from New Zealand called the Kerry 3D data set. And it really is this simple to go from SegWhy to display, even in a CPU bound process, because this is a small file. So here we would download the SegWhy data. I did it ahead of time to avoid any latency issues. And we import SegWhy, import matplotlib, choose the part of the file that we're interested in. And the terminology here would be inlines and crosslines, and then we plot it. So with 3 blocks of code, we're able to get to a seismic section in the SegWhy.io world. What I did was a bit more involved, but potentially is more scalable. Here I'm importing my libraries. I'm writing the specifics, which I can go into with anyone interested a bit later about the SegWhy format. But here I'm doing the decoding. I'm also downloading that same data set and reading it kind of together. And then I'm doing the comparison here. So I'll start from here in, I guess, in detail. So the netcdf file that I'm trying to build, it starts off as a wireframe, let's say, and then I put things into it. So the dimensions for this particular data set would be 3D. So it's inlines, crosslines, and the actual sample data. That's like from top to bottom. With that basic structure of dimensions, I can now assign various pieces of data to these dimensions and then reference that the dimension a bit later, if needed. But as a simple summary of what was done so far, you can have a look at the netcdf structure, which tells you what you've put in, what you've not put in. And I'm probably not doing it justice here, but when we get to X-ray, it'll be a lot simpler. So I'll try to maybe fast forward to the end before we get to the other live coding. So if I just pull up so if I pull this up again. So if we imagine here, this is the kind of the abstraction. So we're starting from some sort of netcdf file that's on disk, and we want to get to an abstraction, then that's really where this comes in. I've done the hard work of converting that SegWhy file to a netcdf file, and it's currently on disk. And one of the nice things about this is that when I read this file in, we can see that I didn't read everything in. I'm just reading like the metadata that's referring to it. So these are the coordinates and the dimensions, what they look like, and these are the data variables. So the actual cube of seismic data is stored in a header called data, and it's referencing 3 coordinates. But some other pieces of metadata, like the X and Y lat and long positions, are only referenced to inline and crossline. Very similar to how like latitude, longitude here only have an X and Y component and not really a Z component, but the actual data itself can have a Z component. So that's one of the very useful ways to utilize netcdf, let's say, to get here. And with 1 line of code, as opposed to, let's say, a few lines of code before, we can get the same seismic section that you would have seen here with effectively an X-ray library. And if we wanted to play with any of that data, again, it could be done in a chunked manner. So if I select one inline and a particular slice of data associated with that cube, we can see the size of that chunk because this is being lazily evaluated. We can see the size of that chunk, the size of the array in memory, its shape, and its data type, all from a more structured format that's on disk than what was previously available, which would have been SegY. The hope is at some point to be able to do that directly from SegY. But yet again, with just a few lines of code, I'll go into the, I think I have a slide for this, so I'll go into that now. Yeah, so you may be asking, well, what's the point of all of that? You know, how do you plot this data that you have? Can you GPU accelerate the plotting process? And the answer is yes. That there are a number of wonderful libraries out there. Ollivierre, GeoViews, Data Shader is perhaps the most amazing, that allow you to take, if I just go back to the notebook, that allow you to take the wireframe structure of the data set that you have on disk and go straight into an accelerated rendering of it, which is quite neat. Yes, so let me finish off the. Yes. So when I had got to this point in the exploration process, I was like super excited because I had something that resembled pandas, which is an X-ray object that was lazily evaluated, and that would allow me to read technically, you know, gigabytes and gigabytes of data, but be able to visualize and play with smaller pieces of it in either cloud environment, my desktop environment. That I was quite excited that I got to this point. But reality check, when I came back to like what the current pipeline looks like, NetCDF is still on disk, and it's duplicating the amount of data that you need to solve the problem. So there was some reflection as to where we would go from here. So something I would like to see would be like an extension to cuDF, or something in the Rapids ecosystem, like a Seismic, let's say, that's purpose-built to more or less go from attribute and array data all the way down to this point, something that's lazily evaluated in memory. Something else would be like if Xarray can read Seismic directly without the need for an intermediary, which would be NetCDF, then much of the problem would already be solved, because Xarray would just be an abstraction on top of the SegY file. Or if something doesn't exist, old adage, you know, maybe you need to go build it yourself. So that's something to look into as well. I just want to say a big shout out to Torin and Ken at the Rapids AI team, and Inzi for doing a lot of the, Inzimam, that is, for doing a lot of the vetting process for my benchmark work. And well, yeah, that's PyDataTT's first talk. I hope everyone liked it, and I guess we could go into some notebooks now.